I've been tasked with talking about the status, uncertainties, and gaps of potential field data for the greater Diablo Canyon region. In particular, I'll be talking about the gravity and magnetic data. So the way I've organized this discussion is to first talk about the status and uncertainties of the potential field measurements and processing, starting off with the gravity data, followed by the magnetic data. And then I will discuss, oops, yes, I see. These are not real, I don't think the people who design these actually ever use them. And then I will talk about the analysis and modeling, the uncertainties of the analysis and modeling of the potential field, the gravity and the magnetic data jointly, because they share the same mathematical DNA with the attendant benefits and limitations. So starting off with the precision of the gravity measurements, onshore, the data are quite precise. Almost all of the data were collected with Lacoste and Romberg gravity meters, which have a precision of 0.01 to 0.05 milligauss. Some of the older data sets were collected with Wardens, still on the order of 0.1 milligauss. So a lot of the anomalies that we're going to be trying to model are on the order of several milligauss. So this is pretty good. We also have marine data. Almost all the marine data was collected on a moving ship. So you can imagine that the accelerations of the ship are a lot larger than the accelerations that we're interested in isolating for gravity. But in terms of the measurements of the precision of these instruments, a lot of the surveys were done in the 1970s. Those instruments have precisions of about 0.1 to 0.3 milligauss. And you also have to keep in mind that this was before GPS, so there are positional uncertainties associated with the ship track data. So close to shore, they are pretty good, 100 feet, say, but as you get farther offshore, it could be a quarter mile off. The other thing to note about the ship data, again, these were done in the 70s. The instruments a lot of them had mechanical damping, so you're only going to see some of the more broader anomalies than you would be able to see with, for example, point measurements. I also put up ocean bottom measurements. This is where they actually lower a gravity meter and make a measurement on the sea floor, and those are just as good as land measurements, but for the purposes of Diablo Canyon, it doesn't really help because those are only right in and around Monterey Bay. Okay, so here's a map of the gravity data that we have compiled and collected in the greater coastal Coast Ranges area. So here is Diablo Canyon, here is Monterey Bay. Keep in mind that these are measurements of the gravitational acceleration, and that these accelerations, we're really interested in that component of the gravity that results from the crustal density distribution. In other words, the geologic contribution. So we have to process the data in order to isolate that geologic contribution through a series of corrections. And here's a list of some of those corrections. Two I'm going to talk about in the next slide on the effect of elevation and topography. The others, for example, the tides, they're small and well predicted. Isostatic correction is very long wavelengths, so that should not be affecting any constraints on crustal density structure. And then lastly, the effect of, oops, the moving platform, the ship track data have accelerations due to the rotation of the Earth that needs to also be taken into account. That can be quite significant. If you want to look at the ship track data, a good way to evaluate how accurate that data is to look at ship track intersections. And for example, for the offshore Santa Maria Basin, some of those ship track intersections disagree by as much as 4 milligauss. However, most of them are 2 milligauss or less. Okay, so however, in general, most of the uncertainty in gravity measurements arises from the elevation. The farther you are from the center of the Earth, the less you weigh. We don't care about that effect. It doesn't really tell us about the crustal densities. And so the effect of elevation is an error in 1 foot in elevation lends itself to 0.06 milligauss in the resulting anomaly. For the data that the USGS has collected, we use a handheld GPS that we post-process. The errors are 1 meter or less, so the resultant error in the gravity anomaly is 0.2 milligauss or less. Another source of error is the terrain correction. You have a big mountain here that's going to actually deflect your gravity vector towards that mass. So we remove that using a terrain correction. That's estimated to be 5 to 10% of the total terrain correction. And here I've gridded up that uncertainty from the terrain correction, assuming it's 10%, with the yellow areas being uncertainties of 1 milligauss or more. And you can see, as expected, those tend to lie within the more mountainous regions of the study area. All right, another source of inaccuracy or uncertainty comes from merging all these various data sources. Here's again that map of gravity measurements. I've color-coded them according to source, and it's very impressive. There's this sea of red measurements that came from the agency formerly known as the Defense Mapping Agency. They collected these data in order to precisely estimate the launch paths of missiles coming out of Vandenberg over here. We are very grateful because it would be very expensive, time-consuming, and in some cases impossible to replicate this gravity data set, which is on the average of a 1-mile grid spacing up to the latitude of 36 degrees, 15 minutes. And why I say it would be very difficult, apparently they used helicopters to just land on peaks, lower a gravity meter, and make a measurement. And I think that might be where people got the idea of the black helicopters. I'm not sure, but we can't do that at the USGS.
What's the big gap, the big hole right?
In here?
Yeah.
That's near Bakersfield. I guess they didn't like Bakersfield.
They don't care if a missile lands there.
It's the armpit of, oops, I probably shouldn't say that. It's recorded, right?
Wait a minute.
Anti-gravity. It's the place to be. In the Sea of Red, actually, there are several different campaigns of data. Sometimes they measured in the same place, and the error that you can get looking at that is on the order of 0.2 to 0.5 milligauss. In some cases, it's a lot larger. So we've gone in and reoccupied some of these data points to try and edit or remove some of these uncertain data sources, but we can't reoccupy all of these data. The good thing is that there's a lot of data, so we can get rid of some of these data points and not really affect the overall regional data coverage. Offshore, we have a combination of gridded data sets from ship track data. We also have data offshore of Diablo Canyon here that was created by digitizing a Bouguer gravity map out of the PG&E basement, digitizing ship track contour intersections. Again, not really sure about how that map was put together, but one thing I can say is if you take all of these data, and you grid them up and contour them, at least onshore, you can contour this to 2 milligauss quite comfortably. To me, that indicates that most of the data is good to 0.5 milligauss or less. Offshore, again, the closer you are to the coast, the better off you're going to be. But I would say that you would need to be a little bit more skeptical of anomalies of, first of all, narrower wavelengths because of the mechanical damping of some of those shipborne meters, and also the locational errors. So I would say probably not good to more than 5 milligauss. Okay, so this is an isostatic gravity map that has removed the long wavelength components associated with isostatic compensation. These should reflect density variations in the upper to middle crust, and certainly the pattern of highs and lows that we see here match pretty well with what you would expect from the surface geology and from drill holes. I do want to point out some pitfalls in just looking at this map and modeling it that arises from topography composed of materials that are significantly less dense than the crustal density that we used to produce this map. So I'm going to show you an example of this north of Paso Robles. We're going to focus in on this area. And you can see on these broader anomalies that there are these narrower lows, generally northeast trending, that are superimposed on these anomalies. If we superimpose these contours on a geologic map, a lot of these high-frequency anomalies correspond to hills composed of either Monterey or Paso Robles formation. So going back to this gravity map, which was reduced assuming that the topography was composed of a density of 2.67, which is like a typical granite. If we process the data using a density of 2.0, which would be a nice fluffy Monterey, we should see a lot of that character disappear, and we do. So just a caution in interpreting some of the narrower wavelength anomalies over areas composed of low-density Monterey. It may not tell you anything about crustal structure. It does tell you about the topography, and it tells you about the density of that topography. So you can get an estimate of the density of the Monterey just by doing this technique. Okay, moving on to the magnetic measurements. For the Central Coast Ranges, we have data collected by airplane, helicopter, and boat. All of the surveys are fairly modern, with instrument precisions on the order of less than 100th of a nanotesla. Keep in mind that the Earth's main magnetic field in this area is about 50,000 nanotesla, so it's really, really quite precise. As with gravity anomalies, we also need to isolate that magnetic field anomaly with respect to the crustal magnetic sources. So we need to remove diurnal variations of the magnetic field. We need to compensate for the magnetic signal of the aircraft or boat that the magnetometer was either mounted on or towed behind. And we also need to get rid of kind of the Earth's main dipole field, the field from the core. You can ascertain kind of the uncertainty by looking at, again, tie line and main line intersections. That's on the order of a few nanoteslas. And we can actually do micro leveling now and get down to uncertainties of less than a nanotesla. So for the Central California Coast Ranges, again, Diablo Canyon is right here. Here is the extent of our magnetic data. The white lines there outline individual surveys, and the shaded area is data that is modern data with flight line spacings of half a mile, flown at a nominal elevation above topography of 300 meters. All collected with GPS, which is really critical because you know where the plane is. So in other words, we have excellent magnetic coverage over much of the Central Coast Ranges. A lot of this was flown in the last 3 years. Okay, now I'm going to focus in on the area around Diablo Canyon, where we have even more detailed data. And this is the magnetic data just from the fixed wing survey that we have. One thing you can do to improve on the delineation of anomalies is the closer you are to the source, the narrower and higher amplitude the anomaly, as shown by the schematic in the upper left. So here, if you look offshore, and if you look in this area here, you will see the attendant delineation and resolution from the helicopter survey that was flown a little over a year ago, and the marine survey that has been collected by the USGS over the last several years. So you can, again, see the delineation of these higher frequency anomalies. One thing I do want to point out, although the marine data is clearly much closer to the source, they were collected along lines that were 400 meters apart. And so in areas where the water depth is less than about 100 meters, we may not be fully characterizing the magnetic field, especially for some of the more three-dimensional sources, and in particularly in like Estero Bay and in this area out here outside of the helicopter survey. All right, now I'm going to shift to uncertainties in interpretation, which are theoretically much larger than any of the uncertainties in the data. It is known that potential field anomalies provide non-unique interpretations, and this is highlighted by this graph here, where you can produce the same gravity anomaly with a shallow, broad, tapered source as with a more deeply buried sphere. This can be shown mathematically. However, in the real world, we have constraints from the surface geology and known ranges of densities and susceptibilities that can reduce this infinite set of answers to a smaller set of plausible ones. And I just want to show you a couple of examples of this. If you know where the surface trace of the fault is and it's juxtaposing rocks of different densities, you can determine the dip of the fault just by where the maximum horizontal gradient is. And an example here, here's a gravity map of the Irish Hills. Here is the Hosgri Fault, and the Hosgri Fault lies right at the base of a very steep gravity gradient telling you that it's dipping very steeply off to the northeast according to the gravity data. We can also locate the edges of these dense or magnetic bodies using this horizontal gradient, and that locational uncertainty will be equal to or less than the depth to the top of that contrast. So for the airborne data, if the magnetic materials go all the way to the surface, the positional uncertainty in the magnetization edges, shown by the black dots from the horizontal gradient, is on the order of a few hundred meters. Okay, we can also glean some information from the wavelength and power spectra of the anomaly. So again, a shallow anomaly produces a much sharper, higher amplitude anomaly, and we can look at the, for example, the noise from a shallow source versus a deep source. The shallow source should have a lot of high frequency noise associated with it. If it's a deeper source, that misfit will be a longer wavelength. Okay, I'm going to show you another major constraint, of course, is the geology. We know from measurements worldwide that neogene sedimentary rocks tend to be less dense, significantly less dense than the basement rocks. We also know that ophiolite also is quite magnetic. And we have physical property information. The white circles are density measurements. The magenta triangles are magnetic susceptibilities. We are also very blessed to have 5 marine borehole gravity surveys in Santa Maria Basin down in here, which gives us information on how the density varies with depth within the neogene section. Okay, I'm going to show you a couple of models now that highlight some of the uncertainties in depth extent. This first model is across the San Gregorio Fault here, which has a nice magnetic anomaly associated here. And we can use the seismic reflection data to get at where the top of basement is, since sedimentary rocks tend not to be magnetic. Here we have a model where we have a magnetic Franciscan with serpentinite along here, juxtaposed against selenian granite. We assume that it goes down to 10 kilometers depth, and we can match that gradient quite well. If we use that same magnetization contrast and extend it down to 15 kilometers, we can still match that gradient, but the dip of that contrast now steepens. One thing that I can say is that it's not very likely that the fault is vertical here if the fault is being delineated by this physical property contrast. Here's another model, set of models that looks at kind of misfits to the gradient. This is along the Rinconada Fault. Again, we know where the Rinconada Fault is. The La Panza granite has a significant magnetic anomaly associated with it. We have susceptibility measurements to help guide the choice of magnetizations, and we can fit this nice magnetic high here with a steep northeast dip. If we dip it farther to the northeast, we are not fitting this gradient. If we dip it off to the other direction, we now have a high in the wrong place. And if we can plot the misfit along this stretch of the model and come up with a best fit dip of about 78 degrees to the northeast. And this just gives you an idea of how sensitive this magnetization contrast is to dip in order to fit those gradients. Next, I'm going to show you comparison of modeling the aircraft, the fixed wing data versus the more detailed data. This is a long model that goes all the way to the San Andreas, but I want you to focus in on this area of the Irish Hills. And one thing that came out of this modeling, which I am assuming that the magnetic material goes all the way to the base of the neogene, that it extends to 6 kilometers depth. These are all variables that could be changed, because I don't really necessarily know that. But what I can do in order to match this magnetic anomaly is have a steep southwest margin that coincides with the shoreline fault, a steep northeast margin that is not coincident with the Los Osos fault, but is a little bit to the northeast. We also can model the Pismo syncline, 3 kilometers or so deep with a steeper southwest margin. Now, looking at a model that Janet Watt has done in essentially the same area, but using the helicopter and marine mag. So again, here's the anomaly I was modeling, has now become a double-pronged anomaly. But she can fit it, again, with ophiolite here, with a steep southwest margin and a steep northeast margin. Again, the northeast margin is not coincident with the Los Osos fault. And she has a prong of ophiolite extending up along the shoreline fault. Again, with the Pismo syncline, it's 3 or so kilometers deep with a steeper southwest margin. So these are robust results that you can glean from modeling the same feature with different resolution data. These are independent. So just an idea of some of the robustness of some of these interpretations. So to sum up, we have excellent coverage of detailed modern magnetic data for the area. I would suggest, however, for the features in Estero Bay, the seismicity features, the marine mag data are a little bit widely spaced and could be improved. Or you could do helicopter. It depends on how much money you have. Gravity data coverage is good for regional analyses, certainly for delineating the dip of the Hosgri offshore, where we have a density contrast, and also for looking at the Pismo syncline. Of course, the marine data could be improved if that is so desired. One thing I think that would really help with the uncertainty in some of these models is more site-specific contrast constraints on physical properties, in particular, how densities and magnetizations might change with depth. I don't think we're going to do borehole gravity in the Irish Hills, but one thing that could be done is to obtain sonic logs for some of the deep drill holes, which would not only benefit the potential field interpretations, but it would also help with the ongoing seismic collection in terms of interpreting that information. And something that we have not considered in the magnetic models is remnant magnetization. And of course, incorporating any of the new constraints that come from the mapping and geophysical data that are being collected in terms of delineating tops of bottoms of some of these bodies would help constrain some of the dips of these interfaces. And so that's all I have. Thanks. Clear as mud.
All right. Thanks, Vicki. I was one of the questions I've had with the work that I'm familiar with done to date, modeling some of these data. I have a big question about how much control we have modeling dips or features at depth. And so you showed a few examples. From areas near Paso Robles, you showed some interpretations that look to be sensitive down to 10 or even 15 kilometers depth. Some of the examples of work that you and Janet have done, in contrast, show maybe a depth of interpretation near the Irish Hills of only maybe 3 or 4 kilometers, or 5 kilometers or so. Can you comment and discuss about how much we should trust or what the uncertainty is once we get deeper than a few kilometers and start to get into the seismogenic crust? I'm just concerned with whether we should, how much weight we should give into interpretations that go deep.
Okay, well, the bottom surfaces of magnetic and gravity anomalies, it's very difficult to ascertain. You can look at the wavelength of the low coming off of a magnetic anomaly, and that will help you look at the depth extent. Now, whether it's 10 versus 12, it will depend on the physical property contrast you use. So if you have better information on the physical property, the average physical property contrast, that will help limit what the depth extent is. I think you can tell the difference between something that's only 3 kilometers thick versus something that's 10 kilometers deep, because you'll start seeing these tails coming off the anomaly, and if you model in a place where it's not being interfered by other anomalies. So but there's some inherent uncertainty. So if, for example, and I've looked at some of the tomography results, unfortunately, they don't seem to really jive very well with the gravity data, which is kind of surprising. I think they kind of see the pismo syncline, but I don't think they have really good resolution in the shallow part of those models. But there's a big gravity high between the Hosgry fault and the pismo syncline, and I would expect to see that somehow in the tomography velocities. And I just don't think we have the resolution in the tomography right now. I don't know if that answered your question, but.
Hey, Vicki, could you go back to the Pismo or the Irish Hills section? I was just wondering, like, how sensitive, and I'm not sure that you can answer this because somebody else did the modeling, but how sensitive is that little sliver of ophiolite along the shoreline fault to the fit of the model? It seems like it could be, it's associated with that really high, that high frequency little squiggle.
This squiggle, yes. It's very sensitive to that,
Yeah.
especially the upper surface, because it comes essentially to the surface. Now, the depth extent of that could be a little bit up to interpretation, because I think if you just had like a sliver that bottomed out there, I think you could still mostly fit that anomaly. Actually, this stuff is going to be presented at AGU on Thursday. Janet has a poster, and she's done some dip estimation, but it's really just based on eye, and it would be nice to kind of do more of an RMS dip versus error. But this steep boundary here is a robust feature in the MAG, whether you're modeling the fixed wing or the helicopter or the MAG. It's very sensitive to near vertical magnetic boundaries.
And we have ophiolites at the surface nearby in a linear array, too, along the fault.
Yeah,
so.
and the one thing about the ophiolite, though, I mean, we're assuming no remnant magnetization, and it's kind of a mixed bag. Some of the ophiolites, most of the ophiolites don't have a very significant NRM that's stable, but the point Sal apparently does, and the direction is almost a declination of east, which is quite different from a declination of north, and it has a dip inclination of 5 degrees, which is really quite different than an inclination of 59 degrees. So it does tweak things considerably. So that is something that we're
Where's that
looking
point?
into.
You said Point Sal? That's
Point Sal, there's a little known master's thesis of a Bruce Lyondike's student that talks about, luckily it gives me not only the direction, but it also tells me the ratio of the remnant to the induced magnetization, and it's 0.4, so it's significant.
so you assume the same is translated up here?
Well, we don't know. We haven't assumed
Oh, okay,
anything
okay.
about the NRM other than it doesn't exist.
Okay.
Can you talk a little bit about data needs for what we had discussed earlier about trying to get more information about remnant magnetism?
Right. So we have collected, actually, I guess Steve collected some samples that we've only just recently been able to measure, and it appears to be some sampling issues. So we'd like to go back and actually drill. Yes, sorry, Steve.
He never could get good samples. Come on.
It's magic. It's paleo magic, right?
I disagree with
Actually,
on the
drill the
record,
samples.
no sampling issues.
Yes, sampling issues. Actually drill them and get a kind of more than just a few hand samples to see if the NRM is important for the ophiolite in San Luis. Uh-oh, it's Walter.
Oh, I was just going to say, Vicki, that in response to some of the questions, a potential field model like the one on the right there that you have expanded could be evaluated, to some extent tested with targeted seismic profiles, so that they could be interpreted jointly. As I'll say later this afternoon, a lot of the seismic data is early 80s, as you're well aware, vintage, and you guys have collected a lot of excellent magnetic and gravity data in the interim. And so now we can come back and target specific features that we'd like to evaluate and look at the dip on these structures with limited profiles. We don't have to do a profile from, you know, from the Sierra Nevada to the middle of the ocean basin. So targeted seismic lines could assist in the resolution of uncertainties.
Actually, I think the combination of all these various data sets has to be dealt with. And in a way, we try and do that with potential field models because of this non-unique issue. But for example, just if some information on where the top of the ophiolite might be would have a lot of help in terms of isolating the component of the anomaly from the deeper ophiolite, because this could be a little bit shallower, it could be deeper. Actually, it can't be deeper than a certain depth because we wouldn't be able to match the magnetization that you need in order for, otherwise you'd have a big low here.
Yeah.
But having some constraints on where these things are going to help in the dip analysis. Even if the seismic data itself can't see the dips there, it will help with the potential field modeling.
I have just a quick question. Given what you were just saying, this is, say, your best interpretation. Is it possible to...
It's preliminary.
Or preliminary. It's a preliminary best interpretation that fits the data. Is it possible to push what is the shallowest the ophiolite can be? What is the deepest? Are there extremes? Can you take to test the uncertainty in the model, or can we push things to the extreme?
Oh, we can.
Limits.
Yeah. And we've done some of that. I mean, if you brought this all the way to the surface, this anomaly would look very different. So you'd have to push it down.
Okay, but that's...
Down to a couple of kilometers. On the other hand, you couldn't have it all the way down here because otherwise you get a big low. But again, it does depend somewhat on what we assume the magnetization to be.
Yeah.
And so we have some induced measurements of the susceptibility, but we really don't have any idea whether the remnant magnetization is going to be important for this area right now.
And I look forward to talking to Janet more about this at AGU, perhaps, but the extent of that ophiolite is a little bit troubling based on the geologic mapping that shows relatively little ophiolite mapped at the surface. So to have an interpretation that ophiolite is the dominant upper crustal rock type in this area. So Janet, I'll be probing you to see if this is really required and how far it is along strike. But it's the uncertainties, you know, our alternative interpretations to requiring an ophiolite in this area, we'd be really interested to see.
Well, I think there has to be an ophiolite in here for the mag. But whether it's down to 7 kilometers or whether it's 3 kilometers thick, we can argue and discuss and do some end-member models that would still fit the observed data.
Yeah.
That makes sense geologically, that makes sense in terms of the physical properties, and makes sense in terms of the behavior of a potential field anomaly. So yeah.
Would a helicopter survey of the Los Osos fault zone improve the dip evaluation?
I would love to say yes. You never know. The problem with, let's see, do I have? Yeah, I don't know if I have something that's blown up enough. The Los Osos fault here, it only coincides with the edge of the this magnetic band right there. And then the Los Osos fault kind of does this little circular thing. And then it might connect with like the Edna fault, and that is now starting to look a little bit better. I don't know if it would help over the Irish Hills per se, but as you get a little bit of cover and you start getting up in here, there are some features here that are not adequately resolved with the closer to the ground survey. So If you wanted to look at that onshore-offshore transition, it would be hard to do with just the marine, with a boat, unless you want to drag the boat behind you. And the other thing I'd also mention is the marine data out here. There is a gravity low out beneath Estero Bay, and it would be interesting to see if that correlates with anything with the seismicity. But again, the ship track data end over here, and we walked the bar of sand. So there's kind of this gap. And I would go with bottom measurements rather than ship track, but they're just a lot more precise. But all of that is quite expensive, and whether that really gives you much bang for the buck in terms of evaluating the seismic hazard, that's up to you guys. But a helicopter survey would be wonderful.